Let us assume for a moment that you just wrote your first hardware design in a new hardware construction language like Chisel. You also wrote a unit test and it passed. Does that mean your design works? Not necessarily. To check whether your test thoroughly tests the design, we want to have a look at the lines of Chisel code that are exercised by it. Currently, the only way to do this is to generate Verilog from a Chisel design and then use the built-in line coverage of a Verilog simulator. However, line coverage on the generated Verilog is not necessarily the same as line coverage on the original Chisel code, and more advanced metrics like finite state machine coverage are just not supported. Most importantly though, other Chisel simulators like the Treadle interpreter and the FPGA accelerated FireSim do not support any coverage metrics at the moment. We want to support many coverage metrics for Chisel code across all simulators, but we want to do so with a minimal amount of work. We thus propose a new abstraction that allows us to implement various coverage metrics inside the Fertile compiler. All coverage metrics that we implement work on Treadle, FireSim, Verilator, the research simulator Essent, as well as a formal verification tool. Now we can boot Linux on a RISC-V core and get accurate line coverage. Of course, most likely you're not a Chisel developer. However, our technique should be widely applicable to other new and old hardware languages and their simulation ecosystem. All our metrics can be used to implement feedback-directed fuzz testing. If you want to learn more, please check out our paper and artifact and come to our talk on Tuesday morning on session 4A. Thank you!
RepCut, superlinear parallel RTL simulation with replication-aided partitioning. RepCut is open source under BSD license. RTL simulation is a fundamental tool for SoC developing, debugging, and validating. However, its slow performance poses significant challenges in modern SoC development. Parallel RTL simulation has emerged as a promising approach. This approach involves dividing the hardware design into multiple partitions and distributing them to different threads. Our profile reveals that data dependency between different partitions leads to frequent thread stall. Previous work only achieves sublinear speedup. Inefficient parallel simulation reduces overall throughput. As a result, parallel solutions have not been successfully adopted in production environment. In this work, we propose RepCut that achieves superlinear parallel speedup. Unlike previous work that partition circuit in a way that retains data dependency and ultimately lead to thread stall, RepCut partition circuit with small overlaps greatly reduce inter-thread synchronization at the cost of extra computation. Profile information suggests RepCut considerably reduces processor idle time. RepCut easily scales on commodity servers with superlinear speedup. Come hear our talk at session 4A for more details.
Hi everyone, my name is Grigory and this is a lightning talk about SMAPIC, a platform that makes architecture prototypes in FPGAs cheaper, easier, more accessible, and more scalable. Researchers and engineers love FPGA prototypes because they provide speed and accuracy much better than in classic cycle-accurate simulators. However, there are three big problems that prevent a widespread adoption of FPGA prototypes in the field. First, they are expensive and necessitate an upfront purchase of tens of thousands of dollars of equipment. Second, they are difficult and require an extensive knowledge of RTL languages such as Verilog. Finally, they are not scalable because of the limited amount of resources in a single FPGA. SMAPIC tackles all of these problems. First, it uses AWS F1 cloud FPGAs, making your prototypes cheap and accessible. Second, it provides open source parameterized RTL code based on BYOC framework, making your prototypes easy to develop. Finally, it distributes your design over multiple FPGAs using novel SMAPIC interconnect, making your prototypes scalable. There is a long list of use cases where SMAPIC shines. This includes multi-socket or multi-chiplet architecture modeling, accelerator verification and evaluation, hardware-software co-design, in situ studies of custom architecture interactions with cloud infrastructure, cost-efficient architecture modeling, remote work, education, and more. Please join us in session 4A for more details. Thank you.
Hello, I'm Min-Sung from KAIST. I'll tell you about our new hardware description language. With functional programming combinators, we can describe the circuits in a composition style. Each combinator automatically instantiates its corresponding sum module and connects the previous output to the next input. However, combinators are not suitable for use in complex circuits with a latency-insensitive design. The existing port combinators combine ports from the same direction, so you need to split the forward and backward ports to express the latency-insensitive design. This is against the purpose of the interface being a communication unit. In this work, we develop latency-insensitive interface combinator. It looks exactly the same as port combinator, but they transform interfaces with both forward and backward ports. Also, they can be compiled to synthesize Verilog and further. As an example, I'll tell you about the TXX module in a NIC. In this module, small sub-modules connected through the latency-insensitive interface. With the latency-insensitive interface combinator, you do not need to explicitly declare backward ports, unlike with the port combinator. Also, we did 2 case studies in this work to test the applicability and productivity. If you come to talk, you can hear more detailed explanations. Thank you for listening.
Hi everyone, I'm Alessandro, and my talk is about EHDL. Network programmers today face a challenge: how to scale network packet processing performance to keep up with the increasing speed of network ports. To do this, software programs will need to carefully leverage the hardware features of the network devices. However, this is a complex task for network programmers, who need to learn and deal with the heterogeneity of device architectures and rethink their software to leverage them. But what if there was a way to turn software programs into tailored hardware designs? That's where EHDL comes in. EHDL is a high-level synthesis tool that can turn eBPF programs into hardware designs. The main advantage of EHDL is that it's based on eBPF, which makes it easier to use than other high-level synthesis tools like AMDVTs. Additionally, EHDL guarantees line rate speed on most applications. It has been tested on 5 use cases with 100 gigabits per second Alveo Xilinx FPGA, and it's been shown to have low energy consumption and uses few FPGA resources, as it's shown here. So there you have it. EHDL is an exciting new tool that can help network programmers meet the challenge of scaling network packet processing performance. Thank you for listening.
Hello everyone, I'm Xiang Yu from New York University. Today I will present our work, CAT, a software-added compiler for packet processing pipelines. This is joint work with collaborators from NYU, Princeton, and Rutgers University. The main motivation of our work aims to solve several pain points for the network programmers. First, the hardware has constrained resources and is all or nothing fit. A program for packet processing pipeline can either run at full line rate or cannot run at all. In addition, existing P4 compilers have multiple drawbacks. For instance, their result might cause suboptimal resource usage, slow compilation speed, and no support for multi-stage actions. Newly developed the programming language compiled to P4, which means they still rely on P4 compiler. Therefore, we developed CAT, a new P4 compiler, to address these pain points through software-added technologies. Inspired by HLS concepts, CAT consists of 3 phases. Transformation can reduce the usage of scarce resources through rewriting a program. Synthesis can do the code generation faster using simpler program synthesis queries. Allocation can fit each type of resources into the backend using IRP or SMT solvers. The experiment results show that CAT is retargetable for both the Fino switch and mention simulator, can generate close to optimal compilation results more quickly, and directly tackles P4 compilations. This is complementary to all newly developed high-level languages. If you have more interest to our CAT compiler, feel free to listen to our talk in the main conference. Thank you very much.